In 6th grade, we use ratios and rates not just for understanding concepts, but for solving real-world and mathematical problems. This standard, 6.RP.3, is all about applying the reasoning you've learned. Whether you're comparing prices at the store or figuring out ingredients for a big recipe, you'll rely on three main methods: creating tables of equivalent ratios, finding the unit rate, or using a graph. These tools turn complicated comparisons into simple math steps. One of the most organized ways to solve a ratio problem is by using a ratio table. The goal of the table is to find an equivalent ratio, a comparison that has the same value but uses different numbers. We do this by scaling. Look at the visual. You start with a known ratio, and then you figure out what number you need to multiply or divide by to get to the known part of your target ratio. That same number, or factor, is then used to find the missing value. Let's see the table method in action with example 1. We know the ratio of dogs to cats is 2 to 3. Now we want to scale up. If there are 10 dogs, how many cats are there? Look at the dogs row. To get from 2 to 10, we had to multiply by 5. We must apply the same factor to the cats row. So we multiply 3 times 5, which gives us 15 cats. The ratio table helped us see the scaling factor right away. A ratio table works just as well for scaling down, as shown in example 2. Imagine you paid $9 for 18 oranges, but you only want to know the cost of 6 oranges. We need to scale down the ratio 18 to $9 to 6 ? To get from 18 oranges to 6 oranges, we divide by 3. Therefore, we must also divide the cost by 3. $9 divided by 3 equals $3. So 6 oranges cost $3. While ratio tables are great for whole number scaling, the unit rate method is the best for solving any problem, especially those involving decimals or fractions. Remember, the unit rate is the value for 1. Our strategy is simple. First, use division to find that unit rate, A divided by B. Second, use that unit rate as a multiplier to find the total amount for any new quantity you are given. This is the most flexible tool in your ratio toolbox. Let's use the unit rate to solve a constant speed problem in example 3. A runner travels 12 miles in 3 hours, and we want to know how far she travels in 5 hours. Step 1. Find the unit rate. 12 miles divided by 3 hours equals 4 miles per hour, 4 mph. Step 2. Now that we know she runs 4 miles every hour, we multiply 4 mph times 5 hours to find she travels 20 miles. The unit rate is crucial for finding costs, as seen in example 4. If 9 notebooks cost $27 and you only want to buy 4, first, find the unit price. $27 divided by 9 notebooks equals $3 per notebook. That's the unit rate. Second, multiply that unit rate by the amount you want to buy. $3 times 4 notebooks equals $12. By finding the cost of 1, we easily found the cost of 4. In the real world, especially with money, unit rates often result in decimal answers, and that's perfectly normal. Look at the banana example. If 5 pounds cost $3.50, we set up the rate $3.50 by 5. Dividing 350 by 5 gives you a decimal, 70 cents. This just means the unit price is 70 cents per pound. You should be completely comfortable expressing unit rates using money decimals. Let's find the decimal unit price in example 5. A 4-pack of gum costs $3. We want the price for 1 pack. The calculation is $3 divided by 4. The result is 75 cents. The unit price is 75 cents per pack of gum. Notice that we can express this as a ratio of 0.75 to 1, even though it includes a decimal. One of the most common ways you'll use ratio reasoning is to determine the better buy. This is where comparing two different rates is necessary. The rule is simple. The item with the lower unit price gives you more for your money. To figure this out, you must calculate the unit price, the cost per one item for every option, and then compare those unit rates head to head. Let's find the better buy in example 6. We are comparing two deals on water bottles. For option A, we divide $2.40 by 6 bottles, giving us a unit price of 40 cents per bottle. For option B, we divide $3.60 by 8 bottles, giving us 45 cents per bottle. When we compare 40 cents and 45 cents, we see that option A is the cheaper unit price, making it the better buy. Ratio problems sometimes involve the total or the whole, which means we have to add the parts of the ratio first. If you are given a ratio of A to B and the total amount of both A and B, you must first find the total number of parts by adding A plus B. Once you have the total number of parts, you can figure out the value of a single part by dividing the total quantity by the total parts. In example 7, we use the part-to-whole method. The ratio of blue to red paint is 4:1. If 20 total gallons are mixed, how much blue paint is there? First, find the total parts. 4 plus 1 equals 5 parts. Next, divide the total gallons, 20, by the total parts, 5. This means 1 part equals 4 gallons. Since blue paint is 4 parts, we multiply 4 times 4, which tells us we need 16 gallons of blue paint. Another powerful problem-solving tool is graphing equivalent ratios. If you plot equivalent ratios on a coordinate plane, they will always form a straight line that starts right at the origin, which is 0, 0. This is the defining feature of a proportional relationship. Each point on that line represents an equivalent ratio, making the relationship visual and easy to analyze. Let's plot the ratio of hours worked to money earned, which is 1:10 in example 8. This gives us our first point, 1:10. Scaling up gives us 2:20, 3:30, and so on. If you plot these points on the graph, you can visually see the line being drawn. The x-axis represents the hours worked, and the y-axis represents the money earned. The line created by the proportional relationship on the graph has a lot of meaning. It doesn't just connect the points we calculated. The entire line represents all the possible equivalent ratios, even if the hours worked weren't whole numbers. The line starts at 0, 0 because if you work 0 hours, you earn $0. If you were to calculate the unit rate, 10 divided by 1, the slope of the line would actually be 10. You can also use these graphs to solve problems without doing a calculation. Imagine you want to know how much money is earned after 6 hours. You simply find 6 on the x-axis, move straight up to the line, and then move horizontally over to the y-axis. The number you land on is the amount earned. Graphs provide a visual way to check answers and quickly estimate unknown values. In example 9, the ratio of pounds x to cost y is 2:1. We plot points like 2,1, 4,2, and 6,3. Now, the question is, what is the cost for 8 pounds? Since the line is proportional, we can follow the pattern or extend the line to the point where x equals 8. If we follow the line, we see that y must be 4. So 8 pounds costs $4. Let's quickly review our 3 most valuable strategies for solving ratio and rate problems. Ratio tables are fantastic for organizing and finding missing values when your scaling factors are simple. The unit rate method is the best all-around tool, as it can solve for any quantity, whole or decimal. And finally, graphs are a great visual check to ensure your ratios are indeed proportional and to estimate solutions. Here's a final application problem using all the skills we've covered. A school trip requires a 3:1 ratio of students to chaperones. For question 1, if there are 90 students, You simply divide 90 divided by 3 to find the scaling factor of 30. Therefore, you need 1 times 30 or 30 chaperones. For question 2, the unit rate of students per chaperone is 3 divided by 1, which is 3 students per chaperone. You are now a master of applying ratio and rate reasoning.